All right, so what I have said so far is that we see that we've got an RLC circuit because we've got a capacitor, an inductor, and resistors. We are told to find IC of t and IL of t, and I noted that usually for a capacitor, oh, I didn't see it was IC of t and IL of t. So I don't know which. No, I do know what we're going to be using because we're doing series, and for series, our formulas have to do with the capacitor. So for the capacitor, we will find the voltage, because the formula for series has the voltage for a capacitor, and then we'll use this formula to get the current after we've already found the voltage. And I said that to get our conditions at 0, for VC of 0 and for IL of 0, you always look at the circuit before the switch action. So before the switch action, we'd say it had been like this for a long time, which means that our inductor is acting as a short circuit, so T equals 0 minus. And our capacitor acts like an open circuit. So since I have an open circuit over here on the right-hand side, I don't have any current over here, so there's no current here. That doesn't mean that there's no voltage. There is definitely a voltage. This open circuit is in parallel with this voltage source. And so now it's I don't like the fact, I mean, I don't know why you would say it's upside down, but to me that voltage source is upside down. I like them the other way. That's not really a thing. There is no right side up for a voltage source. But the 0.1 volts, when it's labeled as 0.1 volts, that means that the bottom is 0.1 volts more, the plus is 0.1 volts more than the minus. So when it's labeled like that, that's what it means. And so that means if the bottom is ground, then that means right here the voltage would be negative 0.1. And so if I am calling my voltage across the capacitor, if I'm saying that the top is plus and the bottom is minus, if that's what I'm calling the voltage across my capacitor, then I would say that VC of 0 has to be negative 0.1, because it has to be, it's in parallel with this voltage source, and so it has to have the same voltage. Let's see, so this is 0.2 volts over here, and this is 0.1 ohms. Are you asking what 0 minus is?
Oh, that's right. I thought we were doing T equals 0.
I am, okay, so this, when I get VC of 0, I have to look at 0 minus. And the same with IL of 0. And so let's go ahead and find out what the current through the inductor is at 0 minus. So at this time, we have current in this part right here, and this is the same. So imagine that I slid this little voltage source around over to here. It just kind of helps me to visualize it. If I did that, then on this side, if I just moved it over here, the plus would be on top. And so I can see that these two are in the same orientation. And so that means that my total voltage is 0.2 plus 0.1 is 0.3 volts.
And you could also just use KVL whenever.
Absolutely, yeah. I wanted to use Ohm's law. I just wanted to use V equals IR, just because I wanted to. There's no rule on what's the right way to do any kind of circuit, because there's always a million ways to do it. And there's many more ways to do them wrong, but there are a lot of ways to do it right. So that's 0.3 volts equals my current times my resistance. Now I do need to pay attention to what direction my current will be going. It will be going this way. So 0.3 volts equals I times 0.1 ohm, or my current is 3 amps. And that is IL of 0 minus, which has to also be IL of 0. So these two things here have to be true at time t equals 0. So now when I redraw my circuit at switch action, I know that these two things still both have to be true. Now, this little voltage source is not going to do anything anymore because it's not connected to anything. So this is now at t equals 0. I have 0.2 volts here. I have 0.1 ohm here. And I know that my voltage here is minus 0.1. Let's see. I need to find alpha and omega to figure out what kind of circuit I have. So alpha for a series RLC is R over 2L. And this is after the switch action. And so I want to look, I don't have another resistor here, but if I had another resistor, like if I'd had a resistor on this branch right here, it would not be a part of alpha. So alpha is 0.1 over 2 times L, which was 0.2. So that makes alpha. Did I lose a resistor? I did. I lost this resistor over here. This is 0.3 ohms. It was not part of my first circuit, but it is part of this circuit. So together I have 0.4 ohms. So alpha is 0.4 over 0.4, or alpha equals 1. Omega naught is 1 over the square root of LC. And L was 0.2. And C is also 0.2. So this is 1 over the square root of 0.04, which turns out to actually just be 5. So just getting some normal kinds of numbers. Okay, so now we have alpha and omega naught, and alpha is less than omega naught, so this is underdamped. So alpha is less than omega naught, so it's underdamped. And so I'll be working with these equations right here, I see that I also need to have omega d. So okay. So omega d is the square root of omega naught squared minus alpha squared. So omega d is 25, square root of 25 minus 1, or the square root of 24, which is 4.9. Now, let's see, I need D1. D1 is VC at 0 minus VC at infinity. So I need to figure out what VC at infinity is going to be. So let's take a look at our circuit again and what it's going to look like at infinity. So I'm going to redraw it at infinity. At infinity, once again, our inductor is going to act like a short circuit, and our capacitor will act like an open circuit. So we can see when we get to infinity, we don't have a current anymore because our circuit is open. But we do have a voltage across the capacitor because just like before the switch, the capacitor is in parallel with a voltage source. There's no current, and so these resistors aren't doing anything. And so everything at the top is all at the same voltage. All of this is all at the same voltage. It's all connected by a conductor, and everything at the bottom is all at the same voltage. And so the capacitor will have the same voltage as the voltage source. So VC at infinity is going to equal 0.2 volts. So D1 equals VC at 0 was minus 0.1, minus VC at infinity is 0.2, so D1 is minus 0.3. D2 is 1 over C IC of 0 plus alpha VC of 0 minus VC at infinity over omega d. Now, IC of 0, we need to be careful with that one. We have not written down what IC of 0 is, but IC of 0 is the current through the capacitor after the switch action. For a capacitor, the voltage you look before switch action, for the current you look after switch action. So IC of 0 is going to be the current through the capacitor right here. And since we just have one circuit that's everything is in series, everything has to have the same current. And so IC of 0 has to be the same as IL of 0, which we found earlier. So IC of 0 equals IL of 0, which was 3 amps. So now I think we have everything we need here. So let's see. So C is 0.2. So 1 over 0.2 times 3 plus alpha was alpha? Alpha was 1 times VC of 0 is negative 0.1 minus VC at infinity was 0.2. All over omega d was 4.9. And so this equals 3 volts. So now I have D1 is right here. So here's D1. Here's D2. I have alpha was 1 and omega D was 4.9. So I have everything I need to plug into here. So VC of T is e to the minus T. D1 is negative 0.3. Cosine 4.9T plus D2, which was 3, times sine 4.9T plus VC at infinity is 0.2. So that's VC of T. To get IC of T, that'll be 1 over C dV dt, or 1 over 0.2. And you need to be careful taking the derivative here. We've got the product rule. So the product rule, if I say e to the minus t is my first function, and my second function is all this over here, if you remember the product rule, derivative of fg is f prime g plus fg prime. So the derivative of e to the minus t is e to the minus t times minus 1 from the chain rule. So that's f prime, and then g, I'll just write this over again, 0.3 cosine 4.9t plus 3 sine 4.9t plus fg prime. So f is e to the minus t. And then the derivative of cosine is minus sine. But I also have to remember the chain rule. So it's going to be, first of all, the minus will multiply times this minus and make it a plus. And then with the chain rule, I would have 4.9 times 0.3, 1.47, sine 4.9t. The derivative of sine is cosine, and I have to remember the chain rule there as well. So it would be 3 times 4.9, which is 14.7. So 14.7 cosine 4.9t. And then the derivative of 0.2 is just 0. And then I could simplify that if I wanted to. I don't want to. Does anybody here want to? No. Okay. All right. So it said to find.
I have a question.
Yeah.
So, like, could you repeat the part about so IL of t is not from, or IC of t is not from 0, it's from 0 minus, or something?
Yes. Okay. So let me do one last thing and then I'll get to that. Okay. So the problem asked me to find IC of t and IL of t. So I need to look and see, do I need to do something else to find IL of t? Do I need to use current division? What do I need to do? And I look at my circuit at t equals 0, and I see that everything is in series. So everything has the same current. So I don't have any more work to do. IL of t also equals IC of t. Okay, so
So, I of 0, like after switch action, and then before infinity, that's the t, right? That's what we're looking for?
yes.
Okay.
Yes. So this is what we just found was, it's basically t greater than 0. I mean, it includes up to infinity. If you plug in infinity, you should get, well, e to the minus t is going to be 0. So we would get 0. So we know it would be 0, but we should get 0 if we take the limit as t goes to
Okay.
infinity. So, all right, but what you asked is really, really important, and it's how we figure out these initial conditions. And so when I took this class, we always talked about 0 minus and 0 plus to help us figure out, what conditions we have. So it is just a fact that capacitors cannot change voltage instantaneously. And that rule cannot be broken. And inductors cannot change current instantaneously. And that rule also cannot be broken. And so because of these two rules, what you always do is you look at your circuit at t equals 0 minus, or before switch action. And all this means, 0 minus means the limit as you're approaching 0 from the left. It still means 0, but it just means we're looking at it coming from the negative side. But since it can't change instantaneously, it has to be continuous. Whatever these are at 0 minus, it still has to be at 0. So whatever I find before I throw the switch has to be the same as what it is after the switch. So this means VC of 0 minus has to equal VC of 0. Or in other words, to find VC of 0, look at the circuit before the switch. Similarly, IL of 0 minus has to equal IL of 0. And so to find IL of 0, look at the circuit before the switch. And those rules, those have to be true. So these things have to be true. So what about IC of 0 or VL of 0? Those can change. Those can be different at 0 than they were before the switch. They can jump. They can have a discontinuity. So for these, when I'm trying to find what they are at 0, I look at the circuit after the switch, because they could be different than what they were before. But when I do this, I always use my values of VC of 0 and IL of 0 that I found earlier, because I know those have to be true. And so if I didn't use those, like for instance, let's say I had not found what IL of 0 was. So I had not found what IL of 0 was. I didn't know that. And then I come back and I look at this and I want to find out what IC of 0 is. Well, if I didn't know that it was already determined, I might mess up. I might look at this and say, okay, I don't really know what to do with that inductor, but I've got 0.1 and 0.3, I've got 0.4 ohms and 0.2 volts, and so I think my current's going to be 2. Okay, it's not. And so the only way to know what it is to know that it is the same current that's going through the inductor because they're in series, and we know what the current through the inductor is because we found it before the switch action. So does that answer the question? All right.